Hello. In this episode, we'll see who is the most powerful Marvel character. This is a fun project involving applying dimensional reduction on something that probably is not finance, but maybe many college students might be interested in. So, the motivation is like if you ever had a debate with a friend over who's the most powerful Marvel superhero. And I came across an article that was a clever application of how principal component analysis can provide an answer, whether you agree or not. And let's see how, right? So here's the reference. The article that I came across was this by Pranay Dev about the power of dimensional reduction. On this data storytelling. So he had a story on how to convincingly show people how what dimensional reduction is doing, and it's all fine. Unfortunately, I couldn't find the exact web address for which data this article was using, nor I could find any code that does. So I decided to take into my hands, and it would be a good example on exercise on trying to see if I can find something on this issue. So this person here, Mr. Dave, had 200 superheroes on 175 superpowers of the data set. I unfortunately couldn't get it, so I went on my own. Unfortunately, Kaggle had one data source here. So I'm using this one. So this is at Daniel R at Marvel-superheroes in Kaggle.com. So you can click download, and then it's a zip file. It has many things, but the last one here, superheroes _power _Marvel CSV file. It has 168 superpowers. 167 superpowers, because the first one is the name. So it's not exactly what the previous article is having, but 168 seems to be good enough. In return, we have more than 200 superheroes. Here we have 667 superheroes. So among the zip file, the superheroes power matrix here, this one basically shows. You can see here, 667, the first row is the header column. So 667 superheroes, and there are maybe some that you are familiar with. Yoda from, I think, the Star Wars, but also there are many Spider-Man and many that maybe somewhere you may have come across. And amazingly, Marvel has agility, many superpowers like dimensional awareness or whole things. And based on the character here, so for example, 3D Man has agility. So if it has agility, it's true, but the ones that doesn't have, it's false. So it's like this. So it's and it has many columns here. Okay, so we are going to use the data. So how can you the debate, and which probably if you have ever gone into debate with your friend over the Spider-Man is the stronger or Superman is stronger, and that it never ends, isn't it? And the problem is that is agility having better than, let's say, accelerating healing? You're comparing apples with oranges. How do you ever settle the debate on this, isn't it? So this is sort of what dimensional reduction is trying to do. Okay, all right. So how we're going to do is that we have the original data of 167 superpower, the columns, and we have 667 superheroes, the Marvel characters in rows. Okay, so we can think about it as an original data of 167 super columns and an observation of 667 of original data. We use an encoder. In this particular case, we'll just shrink it down to one dimension. So dimensional reduction from 167 dimension to one dimension. So we need a 167 by one eigenvector, just one eigenvector. So we shrink it down this as 167 dimension into one dimension. So we transform the data, which we call principal component of 667, all the superheroes, with one measure, one principal component, this value, and see how that value lines up, right? Okay, so I did that, and we'll see in a minute with the program how it works out. So there are many, of course. If you Google the most powerful Marvel character and so forth, you will get many, many hits. Here's just one of them. It's just one of them, and it ranks, it has own favorites. So whatever criteria that may be, Franklin Richards seems to be ranking high, and so forth, isn't it? Legion. Okay. So they are like the 15 top for this particular website that they rank high. Whatever we come up with, and we'll see in a minute. Some of them seems to be in our top like 15, 16 list of here, isn't it? Like Odin, like Thor, or Franklin Richards, Doctor Strange, Captain Marvel. I mean, these people. So we do have about 1/3 overlapping with their one top 15 set, which probably is not bad, given that there are like 600, nearly 700 characters, and out of that we kind of managed to squeeze in our favorite into the top 15 list. And also you can see it here in terms of eigenvector. I spread it out between 0 and 1 randomly, so the vertical line doesn't matter. It's actually just along this line here, the superpower weight. So which superpower mattered the most? Which eigenvector has the largest among the 167 superpower weights? Which one has the highest weight? And it's kind of in an absolute value in the sense that it's a vector, so it can be in the minus direction, it can be in the positive direction, just away from 0, which one has the largest absolute value. And it seems that not many are in this particular set are positive. Many of them are in the negative direction, very far away from 0. And just to name a few here on this frontier: time manipulation, reality warping, time travel, dimensional awareness. Something with time and space manipulation seems to rank really high in the superpower list, or be very important. Okay. Okay. And also, who is the most powerful superhero? So among those 667 superheroes, so we do have the principal component. Again, plus or minus, which one is far away from 0. And what we can see is that like Franklin Richards or Odin and Doctor Strange, these kind of people seems to be ranking fairly high here on the frontier, which some of the websites on this topic seems to agree. All right, so enough said. Let's see how we do it in our program. So I already uploaded on Google Drive, so I'm just clicking and opening it up. So I'm going to use NumPy array as usual, and Panda to manipulate that array. I'm plotting using the pyplot, Seaborn, and NumPy for the eigenvector. So let me just do that. Let me load the data, which is the superheroes power matrix. Again, 667 by 167 matrix, and read it into the Panda data frame. Okay. Let's just check the data if I'm correct. So the shape and the kind of the headers that we have is 667 by 168. It has one more column because of the name. So the name here is one more column. Okay, we're gonna drop it when we do the dimensionality reduction. But the rest of it are true and false. We probably should convert it to a 1, 0, true is 1, false is 0. Okay, so let's just clean up the data. So the data frame hero here is the name, and I'm converting it and call hero to the NumPy file and reshape it to this 667 by just not one, it's just 667 of just a vector. And then the superpowers, 167 of them. So the location other than the name, the columns other than the name, I'm just pulling all this and putting in the data frame X, DFX, and then convert it to a 10. How do I do it? Well, I'm saying the DFX, instead of true and false, convert it as type integer. So now I do this, it's an integer of 667 by 167. I dropped the name. For the DFX name, so let me just have the superpower names, the column names of this DFX. So these are all 167 superpowers. I want to name it later when I get the result. I want to match it and cross-check it. Okay, so the names to NumPy and reshape it to get a shape of 167 names. Okay, if you have any doubts, X names can always check, and then all the 167 names are here. All right. As I said, the correlation matrix are based on the d-mean columns. So we need to subtract the mean and standard divide by standard deviation to standardize the data. So we compute the mean and standard deviation here, and subtract the mean and divide by standard deviation. So just to confirm, the mean of the DFX here are like 10 to the minus 17 of something, so it's close to 0. And the standard deviation, 0.999 something, so it's close to 1. Okay, so standard deviation 1, mean 0 variables now here. Okay, and if you're curious, you can plot the correlation. There's the, for Panda data frame, you can type the CORR, and we are going to use the Spearman correlation of the absolute values. We don't care the positive or negative here. So let me just heat map of the correlation. See all the superpowers and here. And some of them are correlated, some of them are not. I guess they're not superly many strong correlation. The darker greens are strong correlation close to 1. Many of them are just weakly correlated. And let's convert that X into the NumPy variable and compute the matrix multiplication of transpose X of X, which gets our correlation matrix. And the eigenvalue is very easy. The linear algebra package of EIG, the eigenvalue, will get us our eigenvalue and eigenvectors. The V is the eigenvector. I sort the largest eigenvalue first, and then, okay, so we have all of them. And then I'll just pick the largest eigenvector here. V1 is my largest eigenvector. Okay, so V1 is the largest eigenvector, and that will be here. Just one eigenvector, 4-dimensional reduction, isn't it? While getting the principal component is interesting, it's also interesting, well, this is the weight that we are going to multiply to this original data, meaning to each of these vector is multiplied to the 167 superpowers, right? So which one is the highest weight? And again, it can be a very large negative weight or can be very positive negative weight. Probably the absolute value is what matters the most. But I also compute the signed one in terms of the rank. So it's merely I'm sorting it NP sort, the NumPy sort function. And I get the index from the arg sort. So, and then I have a rank because I want to know which one was the largest one. So, and I create a data frame to be convenient. I put the superpower name, the rank, and the value of that eigenvalue, eigenvector, meaning the weight or multiply on that particular superpower. And I can do the same thing to the absolute value of V1, and this is probably more meaningful. So we do this. So the top 10 ones are here. For the signed one, I don't know what's here, but it seems the absolute value ones, reality warping, time manipulation, dimensional awareness, time travel, many things relate to time, teleportation seems to be related to time here. Okay. So we can actually have a scatter plot. Here's our scatter plot. What I'm basically doing is I have the y, which is just doesn't mean anything. I could have plotted in one line, but then all these dots will overlap on one line. So I'm just giving a slight random number between 0 and 1, so they spread out vertically. The real deal is the x variable, which is the weight values here, right? And here's the signed one, so it could go on the positive side or could go to the negative side. It turns out relative to 0, it's more likely to be far away on the negative side. So D seems to be an absolute value, the more dominant one than the positive ones. All right, and you can see a whole bunch of here. You can pick out your favorite by looking at the DFV one, superpower of which index you want. The highest one is the 0. The smallest one is the 666. And then here, who is the most powerful Marvel character? That relates to here the principal component. Which one has the largest absolute value? All right. So that in the rank. So there are 667 Marvel characters, and they all have a number based on this one principal component. Okay, so let's see. That is the multiplying the x with the v1, the eigenvector. And we sort them according to the larger to the small principal components. You have to sort and get the index so that I can create a data frame that has the superhero name, and then the rank, and then the principal component value. Okay. So which one is the top 20 in our list? So it will again go in the very large negative values. Spectra, Man of Miracle, One of All, Living Tribunal, Mr. Mixed Stick, Franklin Richards, sounds familiar. Amazo, Dr. Manhattan, Odin also sounds familiar. Galactus, Martian Manhunter, Thanos sounds familiar. Legion, Doctor Strange, and see Captain Marvel, right? So we got a whole bunch of list of it, and if you have curiosity, I don't know why, but Spectra seems to be top of it. Right? We can also plot it in a scatter plot, just like we did with the eigenvectors. We can do the same thing with the principal component, and here you can see, again, I spread it out vertically, but really the horizontal line is where it stands is what matters. And relative to 0, there are many that are on the positive side, but not too far from 0. But some of them go very far on the negative side, okay? Like Franklin Richards, Odin, Captain Marvel, isn't it? Yeah. So Doctor Strange is here, for example. Spectra is here, so way out here. And yeah, if you have doubt, here was the list that I looked up. I think we just saw it. I guess this is the page, isn't it? So here we had many actually. The Marvel fandom has also their own favorite ranking. So Marvel's ranking is here. I think I pulled out that ranking here on the file, but here's the whole list of it. And again, our favorite, Galactus, Franklin Richards, many of them seems to be our list. Seems Odin seems to be on our list as well. I think I did have it on here. So Molecule Man. So on this website, the 50 most powerful Marvel characters were like Franklin Richards, Legion, Captain Marvel, Doctor Strange, and these people. And on the Marvel fandom website, they had like Franklin Richards, Galactus, which was also on our list, and Odin, and these people. So, well, not too bad, isn't it? Out of 667, we managed to agree with the website for some of our favorite picks. Right? So this is how we can apply the dimensional reduction, the principal component analysis on our cartoon or Marvel characters. Right? Thank you for watching this video.